Chapter 12 is covering nuclear energy, and the case study at the beginning on page 254 is going to cover the history of nuclear power plants. So we'll be going over the introduction to nuclear power, nuclear fission, and some of the pros and cons of nuclear energy, and the safety issues and the storage of radioactive waste will be tomorrow night's reading. So nuclear energy is energy that's released by nuclear fission or fusion. And it was originally discovered, at least nuclear waste. Marie Curie is the most famous, but also Rutherford. And initially, it was us studying nuclear fission as the use of a weapon. Nuclear fission is when you take an atomic nucleus and it's split into two smaller fragments, and this releases a large amount of energy. Fusion is when you join two lightweight atomic nuclei together to make one new, heavier nucleus, so a new element, really. And it also is accompanied by the release of a huge amount of energy. We use fission. Fusion, we can't really control the energy. So fusion is like the energy of stars. That's how stars are born. Like that's what's going on in our sun right now. They're fusing atoms together. And we can't really control that energy. So nuclear fission, splitting the atom, that's how we make our power. And as a quick review, if you look at an atom, the nucleus is made up of neutrons and protons and a dense nuclear center. And then you've got your electrons that orbit around the nucleus. For neutral atoms, they're going to have the same number of protons and electrons. And the number of protons doesn't usually change. The number of neutrons can change because we have what we call different isotopes. The atomic mass is the sum of the protons and neutrons. We don't add the electrons in because they're so small, they don't really contribute much to the mass. And the atomic number is the number of protons per atom. And again, the number of protons don't really change, so each atom has its own atomic number, and that should remain stable. In an isotope, that's when you have more neutrons than protons, and that's a different version of the same element. And isotopes are one way to track radioactive decay. An unstable isotope is something that goes through radioactive decay. And radioactive decay is when energetic particles are raised from an unstable nuclei are emitted or are sent out. So, for example, uranium-235 will decay over enough time to make lead, Pb-207. Every isotope is going to decay based on its own half-life. And we use isotope information to look at past climate data. We use it to date things. We've heard people talk about carbon dating or dating of even older materials. So we use this isotope information for dating. And it also tells us how long something might be radioactive. We'll look at what's called the half-life. So if you look at the half-life, it's how long it takes a sample of an isotope to half of it to break down. So iodine-131 breaks down in about 8.1 days. So there'd be half of a sample of iodine left. Xenon breaks down in about 15.3 days. If you look down and you see something like plutonium, it takes 6,600 years to break down half of a sample. And radium, 1,600 years. Cesium, 137, takes 30 years. So when we're looking at radioactive material, our uranium, primarily that's used in nuclear power plants, we need to look at how long it'll take to break down. And we will do some half-life problems in class. When we look at the nuclear fuel cycle, it's not just the radioactive part. We need to look at what's involved in making the fuel and then creating the energy. And so first of all, the material used in nuclear power plants is uranium-235, which means uranium has to be mined. So all the environmental problems we talked about with mining apply to nuclear power as well, because we have to get the uranium from somewhere. When we have mining, we know that we have deforestation, we have soil erosion, but the uranium tailings aren't going to be, filled with acid, they aren't going to produce necessarily acid mine drainage. They're not going to have heavy metals necessarily. We're looking at the tailings that are going to be a low-level radioactive waste. So if we have contamination from a uranium mine, you're looking at radioactive contamination of groundwater, not just like heavy metal contamination. At which point we go through the enrichment process. Then we make the fuel assembly. So usually the rods, but sometimes we use pellets. So we make the nuclear reactor pellets, we make the fuel rods, and we take them to the nuclear power plant. At this point, we have all of this low-level radioactive waste. At the nuclear power plant, the uranium is split into different atoms, producing energy. That energy, of course, heats up water. That steam, the steam released from the hot water, moves a turbine, and the turbine powers a generator. The spent fuel is temporarily stored on site, and then we're still looking for safe ways to store it for 10 half-lives. But that would be high-level radioactive waste. Some of it can be reprocessed and reused a few times, so that's good. And then the water that's also used has to be usually recycled. So again, nuclear fission is the splitting of the atom, and uranium-235 is what we're using in nuclear power. If you look at a nuclear power plant, you've got your fuel rods here, your fuel assembly. As you're splitting the atoms in here, it's heating up, and we've got water going through the cooling tubes. So this hot water makes steam. The steam powers that turbine, moves a generator, produces electricity. Similar to how when we burn coal, we, produce steam that moves a turbine that powers a generator that makes electricity. The liquid so when the steam condenses again, it's either brought right back into the heat exchanger, or it's sent to a cooling tower first to cool off, and then this sent back in to the heat exchanger to become steam again. So in the best nuclear power plants, the newest ones, all of this is a closed loop system. Some older nuclear power plants have a cooling lake, which it's easier to contaminate groundwater with. So the Turkey Point, I believe, in Miami has a cooling lake and not a cooling tower. If you use breeder reaction is when uranium-238, which is not usually fissionable, is converted into plutonium-239, and that is something that you can break apart with nuclear fission. So if you have uranium-238 available, you can also convert that to a different element to use for nuclear power. So what are some pros? There's less of an immediate environmental effect compared to fossil fuels. So mostly nuclear power plants put off water vapor. They don't really put off greenhouse gases. So there's no carbon dioxide. You might be able to generate hydrogen fuel as well using nuclear power. So when it's good, like when it's running well, like nuclear power is amazing. It does great things. It just, when it's bad, it's really, really bad. It's expensive to make a nuclear power plant. So investing in nuclear energy is a multi-billion-dollar enterprise. There's many steps that do require fossil fuels, all the way from mining to the disposal of the energy. So even though it doesn't use fossil fuels in its factory or in the power plant, it will ultimately use fossil fuels during the mining and transport. And we don't know what to do with the radioactive waste. And the radioactive waste is what we'll be mostly talking about in tomorrow's reading.